Hey guys, so today we're going to do another practice problem for a multi-step heating or cooling curve calculation. So again, we have all of our givens, and the first thing that we want to do is draw a quick heating or cooling curve. So for this problem, we want to calculate the energy needed to cool a substance. So I want to draw a cooling curve, which means temperature is going to decrease over time. Alright, so we know that the melting point is going to be the same temperature as the freezing point. It takes the same amount of energy for a substance to melt as it does to freeze, so those two processes occur at the same temperature, which is going to be 0 degrees Celsius. The boiling point and condensation point are also going to occur at the same temperature because they take the same amount of energy. Alright, first thing, again, that we always want to do is figure out where are we starting and where are we ending on the graph. So we are going to start at about 37 degrees Celsius. Let's say that's right here. And we're going to cool this substance down to a negative 15 degrees Celsius, which is right here. Again, the number of segments that we pass through will tell you the number of steps that this problem will be. So I'm going to have this first segment here, which I'm going to call Q1. Next, I'm going to have my plateau. I'm going to call this one Q2. And then lastly, I have another temperature change, another diagonal from here to here. I'm going to call this Q3. Alright, a few other important things to know for the graph. We need to know what state of matter we're in. So at the highest temperature, this substance is going to be a gas. My phase change from a gas to a liquid would be the heat of vaporization. Next, it becomes a liquid. The liquid fuses into a solid. So knowing those few things will help us when we do our calculations. So let's start with Q1, my first segment. First thing we need to do is pick out our equation. So segment 1 has a temperature change. Anytime we have a temperature change, we want to use MCAT. Q is equal to MC delta T. The mass of water is 7.5 grams. We already said that segment 1 is a liquid, so I'm going to use specific heat of water as a liquid, which is 4.18 joules per gram degree Celsius. And then remember, we need to treat each segment like its own problem. So looking at segment 1, the change in temperature would be 37 degrees Celsius. Segment 1 starts at 37 degrees, it ends at 0 degrees, so my change in temperature is 37 degrees Celsius. For now, keep all of your temperatures positive. It's going to make things much easier. Alright, let's go on to segment 2. So segment 2 does not have a temperature change. Segment 2 starts at 0 degrees Celsius, it ends at 0 degrees Celsius, so if there's not a temperature change, I can't use MCAT. We already said that when a substance is changing from a liquid to a solid, I want to use the heat of fusion. So mass times the heat of fusion. Again, my mass is 7.5 grams. Heat of fusion for water is 334 joules per gram, which gives me 2,505 joules of energy. Alright, lastly, segment 3. So again, first step is to pick out your equation. I have a temperature change. I see temperature is decreasing. Anytime I have a temperature change, I'm going to use MCAT. Again, we have 3 specific heat values, so we want to make sure that we're using the right one. Segment 3 is a solid, so I'm going to put in the specific heat of water as a solid, 2.06 joules per gram degree Celsius. And then lastly, change in temperature. So again, we want to treat each segment like its own problem. Segment 3 starts at 0 degrees Celsius. Segment 3 ends at a negative 15 degrees Celsius. So my temperature decreases by 15 degrees Celsius. 231.75 joules. Alright, lastly, just like with our heating curves, to get the total amount of energy that this takes, I'm going to add Q1 plus Q2 plus Q3, which gives me 3,896.7 joules of energy. But there's one extra thing you can't forget for cooling curves. If water is cooling, it is exothermic. If you have a glass of water and you want it to freeze, the way that we get it to freeze is that heat energy has to leave the water. If heat energy is exiting, it is exothermic. And remember, anytime a process is exothermic, Q is negative. So the last step anytime we have a cooling curve is you need to add that negative sign. Again, the sign of Q tells you which direction energy is flowing. Since this is a cooling curve, energy is exiting. So we need to add that negative sign to show that the energy is leaving the water.